To a new week. This is week number 6 already, and wow, we are already a third of the way done with the semester. It just goes like that. Just a couple announcements here before we get started today, and then we'll jump in. Obviously, I graded the exams. I found out that have you guys ever been to a place called Cane's? They serve like chicken and all that stuff. Well, I found out that they're open until 2 a.m. Down in Fullerton. So on Thursday night, after I collected all the exams, I went down there, and I think the staff was like thinking I was weird or something, because I just kind of sat there with the stack of papers for about 5 hours, and I didn't leave till like 1:30 in the morning. I was like getting lots of chicken, and it was getting me in a good mood. So that was helpful for grading. And I just graded like crazy that night. And then I had a few left over. So Friday I finished up. I got them done pretty well. And one of the reasons why I think I got them done pretty smoothly was actually overall, I was pretty happy with the results of the exam. Of course, when people do well, that's good for you guys, but it's also good mood, and then the food makes it even better for me. So anyway, it was a relatively nice grading experience for me to get those done. Now, not everybody is probably feeling great about the test. I'm sure that there's a whole range. In fact, there is a whole range. I had several people who ended up over 100% by the time we do the extra credit, and a lot of people solid 80s and 90s percent wise. So that was really good. But of course, there was also people down below 50, for example, which is really not where we want to be. And I know nobody's really that happy about that. What I'm going to encourage you, if you didn't do as well as you would have liked on the exam, definitely take a look at the comments that I made on your paper, and any places where you could see that, yeah, I obviously messed this up, or I didn't understand it very well. Take a look at the solutions that I've posted in Canvas and kind of side by side, line them up and ask yourself, okay, let's just make sure that I could get 100% on this if I was asked to do it again right now, so that you make sure that any misconceptions you may have had, that you do address those. If after looking at my solutions and setting your exam side by side with it, you're still a little bit hazy about it, not quite sure what was going on, then by all means, please feel free to come to my office hours and I can look at it with you and kind of talk you through it. I'm not going to go over the exam in class. Like I said, a lot of people did really well on the test. I don't feel it's really necessary to kind of go over everything there. But if you have a personal issue or challenge with any of the material and you would like to talk to me about it, I definitely encourage you to do that. You definitely can feel free to stop on by. Yeah, so I added all those extra credit points up and everything else. Keep in mind also my grading scale is not quite a standard scale. It's a little bit stretched out. So to get an A in this class, you're going to need 87.5%. As long as that's at least for an A minus. So of course there's A minuses. The full grading scale is in the syllabus again, so you can take a look at that. To get at least to a B minus, you need 75, and to get to at least a C minus, you need 62.5. So there's a lot of people up there on this exam in a pretty good standing. Now, before we all crack open the champagne corks and celebrate, have a big party about all this stuff, I do want to sober you up just a little bit by reminding you actually of something that's really true in 20 years of teaching this class, which is that most students will generally tell you that the first exam in Math 250B is somehow, it's more computational. It feels a little more like calculus. And so in that sense, it's more familiar to people. Sometimes what I find with this class is that people will struggle more later on when we start getting, well, you watched my video already, a lot more abstract stuff where writing things down carefully becomes really critical, and it somehow feels much more like writing essays and not so much like a traditional math class. So some people will find that to be true. Not everybody. I've had some students who just constantly improve through the whole semester, but it does take a dedicated effort, especially with this more abstract stuff that's coming. So try not to rest on your laurels too much. I really appreciate all the hard work up to this point, and I can see that it has paid off nicely for many of you, not for everybody, but for a lot of you, it's paid off nicely. But let's keep up the good work. Let's really keep up the good work as we move into the sort of the middle part of the semester here. Over this next month, we're going to be talking about chapter 4. So chapter 3, which was on determinants, yeah, that was the shortest chapter in the book. Guess which chapter is the longest chapter in the book? It's chapter 4, which we're starting now. You guys have already watched a 78-minute video on it, and that's just the tip of the iceberg. So there's quite a bit. We're going to be spending several lectures here trying to understand this idea of a vector space. And so it's going to feel a little bit foreign. But anyway, not to take away, the first exam was awesome. Overall, you guys really, really did a good job. I was the average was about 62%, and that was before I even added the extra credit. The extra credit was most people got about 7 points, 6 to 7 points between the extra credit. So that bumps the average up close to 70% for this exam. So I was happy with that. And the grading, as I said, was better than average, I would say, from my perspective. So I really appreciate that. Yeah, so, and I also pretty much everybody watched the extra credit video. I was a little worried whether I would get everybody to do that, but everybody did it. So I appreciate that. I've tried to put a little recap of that video over here on this sideboard. I'm going to talk us through this for a minute. And then I guess I forgot to write down my warm-up problems. We're going to do a couple of warm-up problems here. And then we'll do some group work. And you don't have anything due tonight. There's no homework for this evening. But I will have office hours tonight if anybody does want to talk either about the exam or about the next homework. What I can tell you is that your next assignment is due on Thursday night. I will take a little bit of time, I hope, on Thursday to take questions in class, but it's a pretty long assignment and I'm not going to have time to do that much of it in class. So be ready to either come to office hours or shoot me an email with some questions. I would definitely not wait until Thursday to start Thursday's homework. In this case, I would try, if you have a little time later today, to get a jump on it, or you really will be up late Thursday finishing it, I think. That's just because we have lots of different examples of vector spaces. And every time we have a new concept in this class, whether it's forming a span or testing for linear independence or finding a basis for something, these ideas we're going to be exploring in chapter 4. Every time we have a new idea like that, well, we're going to have to look at what it looks like for matrices. And then what does that concept look like for polynomials? And what does it look like for calculus functions? And so to really get the hang of that, I have to assign a reasonably good number of homework problems so that you have practice in all of these different contexts, because the notation, let's face it, it looks different depending on which universe you're working in. And if I don't give you enough homework problems, you won't have the chance to get good at seeing those concepts in each of these different places. Okay, I'm not trying to just be, you know, a heavy homework person. I only do it because I think it is needed. It's really important. So let's just get into it here. I'm going to just remind you, chapter 4 is all about vector spaces. You can't take a class on linear algebra without learning about vector spaces. Longest chapter in the book. There's a lot to say here. Starting off here, I've got a little bullet point list of some of the most familiar vector spaces that we're going to be looking at. And a vector space, as I tried to describe in that video, is kind of it's an abstract mathematical apparatus that satisfies a whole bunch of rules. Actually, I have all of those rules. I know some of you are trying to write down that recap, but I'm going to cover it up for just a second because I want to show you. Let me see if I can get my screen to come up here. I'm going to cover, I'll put this back down for you guys in a second to see it. But this is our Canvas page, and I just wanted to remind you about vector spaces here. If we go to Files, which we often do on the Canvas page, there is a folder called Special Handouts down here near the bottom. If we click on that, the handout that's way at the last one, the bottom one here, this is, when it comes up, these are the axioms of a vector space. This is literally the definition of it. But it takes an entire page to write it out. And most of it is relatively boring because most of these axioms, like commutativity of addition, associativity of addition, distributivity of scalars over addition, and so on and so forth, these algebraic axioms, well, they're just the same algebra axioms that you've used your whole life, right? The fact that 3 plus 5 is the same as 5 plus 3. Sure, we know that. The fact that parentheses don't matter when I add things together. These are kind of natural axioms. Now, if you, or when you change your major to math by the end of this semester, and you decide you're going to take Math 307, which is our math major version of sort of more advanced linear algebra, they're going to give you some examples where everything is weird. The way you add things together is weird, and the way you do scalar multiplication is weird. And in a class like that, sure, maybe some of these axioms are a little more interesting, and you actually have to think about each one of them. There's 10 of them here, right? But in our class, in this class, I'm not going to be throwing weird vector spaces at you. I'm not going to be asking you to do addition or scalar multiplication in a weird way. And for that reason, most of these axioms are just going to be hiding in the background all semester long. Okay, the main important things about a vector space for our purposes are, first of all, we have a set of vectors. They may not be traditional vectors that you would have seen in physics or in calculus. They could be anything. They could be pieces of fruit. They could be colors of the rainbow. It could be anything, really. And then we have two operations only in a vector space. Namely, we can add vectors together, and we can do scalar multiplication on vectors. A scalar multiplication just means taking a number and multiplying it into a vector. Those are the only two operations we're going to allow ourselves to use when we're in a vector space. So for example, I realize that we all learned just a couple weeks ago how to take n by n matrices and multiply them. Right? We all learned how to do, A times B. We did it right here like 2-3 weeks ago. Well, we're not going to do it anymore. When we're working in vector spaces, I'm sorry, we cannot do regular matrix multiplication. All we can do is addition and scalar multiplication. We're going to strip away everything else. Right. And all of these axioms just involve addition and scalar multiplication. The two most important axioms in this whole big list are the first two. They are the closure under addition and the closure under scalar multiplication. That means if you add two vectors from your vector space, the result needs to be another vector in your vector space. So if I take banana plus carry, that should not be equal to green, right? It does not make sense that I take two fruits and I add them together and I get some object that's no longer making sense in that universe. So the results of doing addition or scalar multiplication need to stay within whichever universe, that we're working in, whatever vector space we're working in. That's critical. So A1 and A2, closure under addition and scalar multiplication. The rest of these axioms generally will be in the background. I could give you actually a good reason why they're going to be in the background. I can give you a really good reason why they're going to be in the background. It's because the rest of those axioms are going to get inherited by a subset S from an already pre-established vector space V, one of these. These are the universes that we will be working with, right? Rn, or the M by N matrices. Notice that since I'm not doing matrix multiplication, it's okay that we have matrices that are awkward sizes. They don't have to be square sizes because I'm not going to take a 4x2 matrix times a 4x2 matrix. I'm going to take a 4x2 matrix plus a 4x2 matrix. That makes sense. I get another 4x2 matrix, right? So we can restrict ourselves to n by n matrices. That's Mn of R. In my video, I also talked about polynomials. We're going to be seeing those. These are expressions that look like, powers of x added together, like a constant term a naught plus a1 times x plus a2 times x squared, and so on. Polynomials of degree less than or equal to n. So there's some maximum power of x here, right? Well, that's another reason why it's important that we're not multiplying the vectors together. If I took x cubed times x cubed, if n was 3, and I took x cubed, if I was allowed to take x cubed times x cubed, I would get x to the 6th, which no longer has degree less than or equal to 3. The degree just fired up to 6, which means it wouldn't have been closed under multiplication. So we don't want to look at that. We're only looking at addition and scalar multiplication. So polynomials of degree n or less. And then this last one is C of I. This is calculus functions, the way you want to think about it, like e to the x, sine of x, 3 divided by x squared plus 5, stuff like that. Calculus functions here. And that is another vector space. My point is, each one of these, those 10 rules that I just showed you, they have technically been verified for each of these. So 10 rules were verified here, 10 rules were checked here, checked here, checked here, checked here. For each of these, somebody, sometime in the distant past, verified the 10 vector space rules. And so we're not going to do it because it's boring, right? We're going to take it for granted that these 5 bullet point structures really are vector spaces. They are satisfying this mathematical apparatus that we're going to be exploring. But these are not really what we're interested in. These are just the universes that are in the background of the problem we're solving. Let me show you what I mean. Let's say I want to solve a differential equation. That sounds like something we do in Math 250B. What if I wanted to solve, got something here just off the top of my head. Let's just say I wanted to solve something like that. Okay, you don't need to take notes on this. Just kind of follow along with me for a second here. The solutions to this differential equation, they are calculus functions, but it's not all calculus functions, right? There's only some functions that are going to satisfy this differential equation. And so instead of looking at the entire universe of C of I, what I'm going to be interested in much more than that is a subspace of C of I, which I'm calling S over here. It's just some of the calculus functions. I can draw a nice picture. I did it in my video that you guys watched where I have my vector space, and then inside of it is actually what we care more about here, guys, is S. It's actually the subspace that I'm going to be concerned with. The solutions to this differential equation, that's part of C of I. It's not all of C of I, it's just part of it, and that's the part we care about, right? The solutions to our differential equation is what we really care about. So what we're mostly going to be doing, guys, is looking at the subspaces. The V, the big vector space V here, is just the big ambient universe that you're working in. Maybe it's matrices on one problem, the next problem, maybe it's polynomials. The next one, maybe it's the calculus functions, whatever it might be. But it's really these subspaces inside of a given vector space that we care about. And the subspace, my friends, inherits all of those. I said this in the video. It inherits the commutativity of addition, the associativity of addition, the distributive properties, all of those axioms down the line. It inherits those, S inherits those from V. So that really what's most important are the first 2 axioms, guys, which I called in the handout, I think I called them A1 and A2. It's just closure under addition and closure under scalar multiplication. It's the closure axioms that we mostly care about. And so to verify if you have a subspace of a vector space, you really only have to check those 2 axioms. The rest of the list, already inherited from these well-established vector spaces where somebody years ago verified the axioms are true. But we don't have to do it again. It's just the subset that I have to focus on. So I have a couple examples here. These are both from my video. The first one is n by n symmetric matrices. So remember that symmetric just means that A transpose equals A. We learned that in chapter 2. So in my video, I actually showed that the symmetric matrices, they are closed under both addition and scalar multiplication. I showed it. And because of that, they form a subspace inside of the big universe of Mn of R, right? They form a subspace. They form a vector space in their own right. Remember, guys, a subspace is really just a vector space. It's just a vector space that's within an already established vector space. That's all you have to think about. It's pretty nice. So the n by n symmetric matrices, maybe those are the matrices that we care about in a particular situation. Sure, they form a subspace of the big universe of n by n matrices. But to show that they formed a subspace, I only had to check these two axioms. Everything else got inherited by the symmetric matrices because it was already true for all matrices. If it's true for all matrices, then it's true for some of those matrices. If I make the statement that everybody in California has a valid driver's license, then of course that applies in Orange County too. So it would be true that everybody in Orange County has a valid driver's license. So I don't have to recheck that. I can assume that anything that was true in the big universe V is also true within S. It's just that closure issue under addition and scalar multiplication that might go awry. And so therefore we better check it. Yeah, that's the idea. The other example, this is a big one in the video, is this idea of a null space. And I did check that in the video, I wrote it out. If you take the null space of any matrix at all, it will form a subspace of Rn. By the way, there's a true-false item for Thursday that I think it says it forms a subspace of Rm. That's false. It's Rn that it forms a subspace of. Okay. Null spaces, by the way, I'm not going to do a lot with this today, but just so you know, you've been doing null spaces for a while already. It's just the solutions to this homogeneous linear system AX equals 0. So if I give you, so here's another example of my point. If I look at like x1 plus 2x2 plus 3x3 equals 10 and 4x1 plus 5x2 plus 6x3 equals, I don't know, 8. There's a system of equations, right? I don't care about all of the points in R3. All I care about are which x1, x2, and x3 actually solve that system. And it forms a subspace of R3. Oh, I'm sorry. These should not be 10 and 8. As you can see, in my definition of a null space, the right-hand side vector should be all 0. I should have been putting 0, 0. That's fine. So what you do is you just say, look, I can make a matrix out of that. Here's my coefficient matrix for my system. The null space of that matrix is just the solutions to that system. So if you know how to do EROs, if you know how to circle your pivots, introduce free variables, and solve a system by back substitution, all of which you should know how to do, then you can find null spaces. You can find null spaces. And they are just subspaces of Rn. These are two really good examples of subspaces. Okay? So anyway, in my video, and I know it was a long video, I really appreciate you taking the time to watch that. But I wanted to do a lot of examples of this. And I'd like to do just a couple more right now to kind of warm up with. So let me come back over here. Are there any questions so far? So far, so good? Okay, let's do a couple of warm-up examples here today, guys. I know chapter 4, it takes a little bit of rewiring to think about these problems. But here's what I'm going to ask in these examples, which which of the sets S form a subspace of V? So which of these form a subspace? This is really what I want to ask here. So here is the first one. The first one, I'm going to use the vector space V to be P3 of R. Those are polynomials of degree 3 or less. And I'm going to take S to be the set of P of X, which is an element of V, such that P of X equals AX cubed plus BX. Okay. And there's, by the way, there's a homework problem for Thursday that's very similar to this one. So we'll kind of give you a good model for it here. So my big universe, that's all polynomials in P3 of R. That would be everything of the form AX cubed plus BX squared plus CX plus D. That's like a typical arbitrary form of any random polynomial in P3 of R. But I'm not interested so much in all sorts of random polynomials right now. I only want to look at the ones that happen to have this form. There's an x cubed term and there's an x term, but there's no x squared and there's no constant. So we only have like a part of the form of a cubic polynomial. So the question is this a subspace of V? This is what I want to address. It's either yes or no. Yes or no. And there's a sort of a starting point that I like to use on all problems like this, which is something I talked about in my video, which is, so for the solution, I may not know what the answer is yet, but I'm going to take as a starting point something in my video that I talked about called the zero vector check. Do you remember that? Oh, see, I forgot to mention that over here in this big long list, in addition to the closure of addition and scalar multiplication, there is this axiom A5, which says that every vector space, which includes subspaces, spaces are vector spaces, every one of them has to have a zero vector. It has to have a zero vector. Now, there is going to be a zero vector over here, because after all, P3 of R is a vector space. So P3 of R has to have a zero vector in it. The real issue is that zero vector in S? Is it in S? So let's just check if it's in S or not. So if I write the zero vector in the universe of polynomials, my question is, can I write it so that it has this form? In other words, can I write it as something times x cubed plus something times x? What do you think? The A and the B can be any numbers that you want. So can I write 0? I'm just going to write it as the sort of as the number 0 here. Can I write 0 as something times x cubed plus something times x by choosing A and B appropriately? How so? A is 0 and B is also 0. Exactly. Exactly. My 0 polynomial can be thought of as 0x cubed plus 0x. And that has the right form of anything that's in S. So I'm going to put that this is in S and I'm going to put a check there. That just means that S passes the zero vector check. That doesn't mean it's a subspace. That just means it passes the zero vector check. Remember, guys, if the zero vector check fails, it's game over. It's game over. What I mean by that is that then it can't be a subspace. If you don't have the zero vector in your set, you can just stop working and just say, look, it's not a subspace. In this case, it does pass the zero vector check. So that means we have to keep going, because just because the zero vector is in the set doesn't make it a subspace for sure. If I really want to know for sure, I got to check that it's closed under addition and scalar multiplication. So let's talk about the closure under addition. So I'm going to go on and talk about closure under addition here. What this would mean is that if I take two vectors in S, then if I add them together, does the result stay in S? So this is where you have to invent a little bit of writing. And there's more than one correct way to say it. I'll give you a good model for it, but you can certainly tweak this up a little bit. So I might say something like, let P1 of X be equal to AX cubed plus BX, and P2 of X be equal to CX cubed plus DX, and then I might say B in S. Let those two polynomials be in S. So you're going to want to practice writing these things out very much the same way that I am. It's going to read a little bit like an essay, more than. I don't want to just see, just chicken scratch math all over. It has to be organized very, very nicely. And this would be a good starting point. So I take two polynomials that are both in S. The question is, if I add them together, will the result still be in S? So let's add them together. P1 of X plus P2 of X, right? If I add these together, this would be AX cubed plus BX plus CX cubed plus DX. I'm literally just going to add all of the terms together for both of those polynomials. And what I would like to ask you now is this still in S? Is the result still in S? How do you decide? Well, anything that's in S has to be something times X cubed plus something times X. There should not be an X squared. There should not be just a constant. Just something times X cubed plus something times X. And I think that that's true. I see some of you nodding your head. Yes, it is true, but I want to really make it obvious to the person reading this. So I'm going to put all of the X cubed stuff together in the front, and that's A plus C times X cubed, and then all of the X terms in the back. And now I've really made it look just like the form of what S was, right? So this is a little bit of it's not hard algebra, but it's helpful algebra in order to represent my result in a form that tells me that this belongs to S. Now, if I just stop right here, or if you just stop right here, I will tell you that I will take off points for this. This is not sufficient because actually the main punchline of this has not been written on the board yet. And the main punchline of this is that after I've added these polynomials together, the result is in S. I have to see that. I have to see that you're telling me that yes, I added these polynomials together, and yes, the result belongs to S. If you leave that off, you've missed the punchline, and I take off points. I don't want to do that. So make sure you're adding that on your write-up. Okay, does that make sense to everybody? Do not just take two specific polynomials, by the way. You notice I'm using A, B, C, and D for the scalars. You have to do that. If you use specific polynomials, any critic will just come along and say, oh, well, you just got lucky. Your polynomials just got lucky. Maybe if I tried some different polynomials, it wouldn't work. That would be the critic's point of view. And you don't want that. So you want to keep it very general here with arbitrary scalars, A, B, C, and D. That looks pretty good. Following me okay? Any questions yet? Am I done? What else do I have to do? The scalar multiplication. Exactly. I've got to check that it's also closed under scalar multiplication. So let's do that one right here. The way I like to format this is, does anybody remember what scalar I was using mostly in my video? I was using K for this, right? So K, and I think that's a good choice. You don't have to use K, but I kind of like to use K. Every time you'll see me trying to do that. So K is just a scalar. It's an element of the real numbers. And then I have to take, for this part, I only need one vector. So what I like to do is just grab the vector from above. So P of X be as above. So you can just do that every time when you're on this second part here. Closure under scalar multiplication. By writing that it is as above, all I mean is, well, I'm just taking the same P of X again. And now what I'm going to do, guys, is I'm going to do scalar multiplication I'm going to do K times P1 of X. I'm going to do a scalar multiplication here. So this is going to be K times AX cubed plus BX. I'm going to stop and take a breath. I'm going to look at that. I'm going to ask myself, is this still in S? Meaning, does it have this form back again? It has to be something times X cubed plus something times X. Does it? It absolutely does. And to make it a little more obvious, I might as well multiply the K into the, I distribute the K into the two terms there. And again, please don't stop short on this. Make sure that you tell me the conclusion, which is that that does have the right form to be an element of S. So it is closed under scalar multiplication as well. So the answer to this question then is yes. This is a subspace. This one is a subspace. So it is a yes. We have verified now that it's closed under addition. It's closed under scalar multiplication. Now, somebody this morning, when I did this example, somebody asked me, well, did you have to do the zero vector check over here? Actually, the answer is no, you don't have to do it. It's just that it pays big rewards if it fails, right? If it fails, it's not that much work, right? This zero vector check is not much work. If it fails, then it's game over and you can stop right away. And even if it passes like it did here, it's just one line. You're pretty much just looking at it. So it was worth doing it. But honestly, what's really necessary, this may not be totally obvious to you, but if you check closure under addition, and if you check closure under scalar multiplication, you can tag team those two properties together if they're both true, and actually prove that the zero vector has to be in the set from there. It actually would follow from these two closures. So that's why you don't really need to check the zero vector when it's working. But I just like to do it because if it fails, you just get a really quick answer. You don't have to work very for that. Okay, any questions on that example? We're going to practice a couple more of these. I'm going to tweak this example just slightly, guys, and let's see if you guys pick up on the difference here. Let's take the same big universe V again, P3 of R, cubic polynomials. But this time S is going to be the set of P of X, which is an element of the big universe V, such that, so now I'm going to put the condition here. The condition is going to be this time P of X is equal to AX cubed plus 5X. The only thing I'm changing for this second example is instead of AX cubed plus BX, now I'm going to consider AX cubed plus 5X, and I'm going to ask whether this changes anything. Again, my sort of no-brainer thing to do here is to just go straight to the zero vector check, right? So let's do our zero vector check again. Now, guys, because I'm working with the same big universe V, my zero vector hasn't changed from the first example. My zero vector is still, so the zero vector is still 0x cubed plus 0x. That's still what my zero vector is. My question is that in S? Doesn't look too good to me. Doesn't look good at all, because actually, if I want to belong to S now, I have to have an X coefficient equal to 5. If the thing in front of X does not equal 5, then it's not in S. And so this zero vector is not in S. You don't have to like write anything down about that in terms of like a, convincing me. It's kind of obvious. You just look at it. You just look at the polynomial. It's not in S. And so guys, this is a big no right away. Remember, it's game over if the zero vector check fails, right? So in this case, it's not in the set. So this is a no. This theme, by the way, of replacing A's and B's, which are arbitrary scalars, with more constrained coefficients. That's what I've done here. I've replaced the B with a specific number. Guys, pretty much anytime you do that, you're going to lose the subspace. It's not going to work because this is just too specific. The membership condition here is too hard to meet. You take two things that belong here and add them together, they're not gonna belong there anymore. I mean, you can just see it, 5x plus 5x, that's 10x. That's got a different coefficient, right? So if you had actually tried to just do closure under addition, that would have crashed and burned. If you had tried to check closure under scalar multiplication, that would have crashed and burned as well. You don't have to do any of that though if the zero vector check fails. You can just write that down and it's game over already. Okay, great. Let's try another one. Are we hanging in there with this? Let's do another one. Let's do number 3. Let's switch to a different vector space now. Let's use n by n matrices. So Mn of R. So now I'm going to a completely different universe, right? This is a totally different universe. And what is my S going to be? My S this time is going to be the set of matrices. Notice that since I'm working in a universe of matrices, I'm going to use a capital A for the notation here. Earlier, I was using P of X's because I was living in a universe of polynomials. It's always a good idea to try to make your notations match up with what kind of universe you're in. Sometimes I'll see people write a capital A for a polynomial. I'm like, yeah, you could do that, but it's kind of not natural. I think of capital A as being a matrix. So I want to write that, I want to reserve that notation for this matrix setting. What's my condition here? The determinant of A equals 0. It just means the matrix is not invertible. Right? That's kind of what that means, as we learned a while ago. But again, same question, guys. The question is, does S form a subspace of V? So I'm going to start off blindly without even thinking about it. I'm going to go straight to my zero vector check and start with that one. So what is my zero vector in this universe? What is the vector that, I talked about in my video? It's the vector that when you add it to anything else, it just leaves it alone. There.
The zero matrix?
The zero matrix, exactly. So that would be the matrix. We've been writing it like this, right? 0 sub n, that's just an n by n zero matrix. And my question for you is, what is the determinant of that matrix? You take the determinant of a matrix that's just all zeros, what are you going to get? 0, right? You're going to get 0. That's kind of just, you don't have to say a lot. It's pretty clear that it's going to give you 0. Okay, so that does belong to S. That does belong to S. Great. So we have the zero vector check. This means that since this passes, now I have to go on. I have to think about closure under addition. Remember, guys, don't take this zero vector check too far. If it fails, then it's game over. But if it works, or if it passes like it is here, then we still have to go on, right? We have to check, okay, well, is this set going to be closed under addition? So let's just think about it a little bit first before we write anything down. Do you think it's going to be closed under addition? If I have a matrix that has a determinant of 0, and then I have another matrix that has a determinant of 0, and then I add them together, do you think that the sum of those two matrices would have to still have a determinant of 0? Or could it somehow not be 0? Now, you guys might remember last week, it wasn't very long ago anyway, we wrote down some properties of determinants. And we remember that the determinant of A transpose, that was the same as the determinant of A. That was very nice. The determinant of A inverse, that was 1 over the determinant of A. Nice formula for that too. And then we had the determinant of A times B, and sure enough, yep, that was the determinant of A times the determinant of B. We had all those properties of determinants, right? Did we have anything for addition? Did we have like determinant of A plus B? Liam?
Well, that's the one.
Actually, what I should have told you, what I hope I told you, is that determinants don't play nice with addition at all. There is no formula for the determinant of A plus B. And that makes me nervous that if I want closure under addition to hold, I might be running into a problem here. Let's see if we can make an example. Now, over here, when I was verifying yes, that we have a subspace, I used generic letters. Okay, everybody needs to really pay attention to this. When it was a yes, I used A's and B's and C's and D's. I kept it totally general. But sometimes we have to get specific numbers involved. And sometimes with specific numbers, we see that might not be true anymore, right? And that would be a good way to show it. If I say to you that all Saturdays are sunny, and you know that that's not true, the way you could convince me is you just find one example of a Saturday that's not sunny, and then my statement is false, right? So that's what I would like to think about here. Is there a way to make an example that's specific that doesn't work? So what I want is somebody to give me a matrix here. Let's just use a 2x2 matrix because 2x2s are easy to do determinants of. Alex, can you give me a 2x2 matrix, just your favorite 2x2 matrix that has a determinant of 0? Okay, let's pick a different one. 1, 2. How about I want to make the determinant 0, so can I tweak your?
Yeah, 1, 2, 1, 2.
Let's just do 1, 2. If I do AD minus BC, that's 0. So that's an element of S, right? It has a determinant of 0. And let's see, who else do I want to pick on here? Maxwell, can you give me your favorite 2x2 matrix that has a determinant of 0? Don't use 0, 0, 0, 0.
3, 4, 3, 4.
3, 4, 3, 4. Okay, so that is also an element of S. The determinant is 0. Let's add them together. When I add them together here, just slot by slot, I'm going to get 4, 6, 4, 6. What's the determinant of that? It's also 0, so it's still in S. So I need some different players here. So my problem with this is I am claiming I'm trying to pull a fast one on you and try to convince you that all Saturdays are sunny. And so I give you an example of a Saturday that happens to be sunny. And I say, see, it works. The determinant of A plus B is still 0. So A plus B is still in S. Do you think it's going to always work though? You want to tweak your example?
0, 4, 0, 4.
Even that is still going to work. We need to tweak it a little bit in a little bit trickier way. David?
3, 4, 0, 0.
Okay. How about we do something like that? Let's just really tweak this thing up good. By the way, guys, this takes practice on how to create these examples. So here I've got an element of S. Here I've got an element of S. Now I'm going to add them together. Let's add them together again. So you're going to need your eraser for your notes now. Don't blame me, blame these guys. But add them together slot by slot. I have a 4 and a 6 and a 1 and a 2. All right, if you add those together, and I'd like you to tell me what's the determinant of that matrix. 8 minus 6, which is 2, which is not 0. So guys, make sure that you get the notes down correctly here. This is not an element of S. I have found an example. I have found one example. It doesn't matter if it's true 99 million times, right? If there's 99 million Saturdays that are all sunny in a row, that doesn't mean that all Saturdays are sunny. And all I need is one example that shows that it fails. And so this actually fails, my friends. This one fails right here. This fails. And so the answer becomes no. It's not a subspace because closure, even though the 0 vector check passed, the closure under addition fails, and we've given one example. We've got 30 people in this room. We could have 30 different examples. Each of you could make your own example of matrices A and B, where the two matrices you started with, they are in S, but after you added them together, it's no longer in S. Yeah. Kind of get the idea? You have to make sure that the vectors you start with are in S. If they're not, then of course you can't. If I say all Saturdays are sunny and you go outside on Thursday, well, I don't care what happens on Thursday, right? So you got to make sure that your vectors are in the set S to begin with. They have to be in the right context. Okay, right, let's. Well, I think that's actually pretty good. That's a pretty good example. So we've seen one example where we had to write out the whole verification. We got a subspace just fine. A second example where we got away easy because the zero vector check failed immediately. And now a third example where the zero vector check did pass, but the set still did not manage to be a subspace. Oh, that's pretty good. Are there questions about this? Liam?
So if the first check fails, we don't have to do the scaling.
Correct. I do think that on Thursday's homework, some of the instructions in the book are gonna say, please check closure under addition and scalar multiplication just to practice. But ordinarily, right, as soon as something fails, whether it's the zero vector check or the addition, as soon as something fails, it's game over. You don't have to go on any further. You can just say no and go to the next problem. Okay? Yes, Tony.
Would it be the same if there were negatives or no?
If you had used negatives in your matrix,
Yeah.
that would also, you could make examples with negatives and also get a counterexample. That actually doesn't really matter here. You just need at least one counterexample. I'm trying to give you some tips because, you know, on Thursday's homework, sometimes you're going to be able to get away with a fast no. Or sometimes you're going to be able to get away with a fast yes. If you have the null space of a matrix, it is a fast yes, right? You just, all you do is you say, yep, it's the null space of a matrix, write down what the matrix is. That's what I did in my video, and you win, right? You already win. You just say, yep, it's a subspace because it's a null space, right? So I'm gonna go ahead and pass this out while I ask if there's any other questions on these warm-up problems so far. What I'm gonna do here, guys, I'm passing out a group work. On the sideboard over here, can you see where I've written A through G up there on the sideboard? Those are some hints on these group works questions. What this is 7 problems of just asking you, is S a subspace of V? And before we break up into groups, I am going to have you break up and run around the room and work on these with 2 or 3 other people. Before you do that, I'll go ahead and let you pass that handout around. I just want to make a couple of quick comments that will speed this up for you a little bit, some hints to help you, if you will. First of all, part A, and I know they're still getting passed out. If you look at part A though, it's literally just the one that we just did, right over here. So you don't have to do it. You can skip past that one. For part B, it's asking about the skew symmetric matrices. Now you might remember in my video that you watched over the weekend, I asked you about the symmetric matrices. And in fact, we showed in the video that those do form a subspace. That was a yes. So the only difference with skew symmetric, I put it over here so you could see it, guys. Feel free to refer to this. The only difference is for skew symmetric, remember the definition, A transpose equals negative A. So there's a minus sign. So if you need help with part B, take a look at your notes from the video over the weekend and just remember that you have to tweak them just a little bit because there's a minus sign that you're not going to see in the one that I did over the weekend. Because now you're talking about skew symmetric matrices. Okay, part C, I have a hint to draw a graph of that equation. Part D, oh, I mentioned the word null space there. So take a look at it, see if you can recognize if that's a null. Remember, a null space is a fast yes. A null space is a fast yes. Part E, I'm going to invite you to skip it because I'm going to do it a little bit later today by kind of a different technique. And then I think part F will also be really fast. Okay, remember we have some fast tricks, zero vector checks, null spaces, stuff like that. That should really be helpful. So without further ado, guys, could you grab 2 or 3 or 4 people? I don't care exactly, but there's plenty of whiteboard space up here. My morning class forgot to erase the board back there. I'll erase up here and let you guys go to town. Feel free to get as much of that done right now as you can. Janda will come around and help, right? Thanks. I didn't say anything about it. Huh?
Not exactly.
It's good. Show you what I did. I went hiking. I have beautiful picture to show you.
In regards to Zion, if you
Oh,
talk.
yeah. I've been to every-
How did you do on your midterm?
I did okay.
Good.
Good.
I was gonna go.
That's good.
Yeah, how many points?
It's a drive. I drove it.
With that, 79 with or without extra credit?
With the. How about you?
With extra credit, well, how many without extra credit?
72.
72? Well, I got 82 without the extra credit.
That's really good.
And then with extra credit, 80.
Well, that's really good.
Okay. And no pressure, guys, but this is gonna end up on the YouTube internet world. So please make sure it's all perfectly correct, no mistakes here, or the whole world's gonna know about it. So let's.
Camera.
So this is hiking. Yeah, San Nevada. So, and then I climbed that mountain. And there's even a little bit of snow on it. This one was, this, I hiked in, first night for 2 hours, set up my tent. This was, set up my tent, and then the next morning I got up. Yeah, it was great. So that's what I did to reward myself. For grading events. Yeah. George and Chris, we skipped part A. Remember, we just did part A right now, but I'm sure right up the right.
Hey, I'm part of the group.
Yeah, that's good. Yeah. Yeah. Yeah.
Good job on getting a second.
Thank you.
Nice. Good job. Okay. So for, these are technically supposed to be pre. So I would make that. But you. Yes, because again, if I take. It doesn't change, it's the same as the negative. So it's that box equation and that. That's this is great for practice formulas that you're not gonna need to. You're just gonna get away with it. Same way I did in the symmetric. Yes. But actually, as we you're not. Work for 4, 5, and 5, 6, 7, 6, and then it's like, yeah, you like. Very good start. I'm going to go along and we'll just stay present. And just whenever you get tired, we made it from.
Or that's the zero check, so. Yeah, very.
And folks, that way you go. Same thing, right?
And if I put lines on it. And now I put manual. Oh, same thing, right? So this is always that, just like. That's all. You know, yeah, that's. It's going to. Yeah, but.
If it's just zero interest, right? It's not scale. So I don't know. If you take the negative versus. Right. Zero, so even if you multiply and make it, it's still the same. If it's just the zero, it's really good.
One thing I'm proud of. I said, this me that is hard. Pull the minus out, just to make, and I see that.
I think this.
Just so I can see that this A plus B transpose is equal to the wall. And then when you really want to see. It's okay. I know. Taking this little thing, that's always good.
Yeah.
Before you write. Oh. Maybe go all one minute. I just say no. And I know it takes a bit of experience and practice to make it once in a while. Yeah, so remember that first video? You got probably have somewhere. Yeah, I did it. I sit on pill. The regular excuse.
So.
I'm assuming. You guys doing okay here? Okay, sounds good. So we're gonna, what you're gonna want to do here, guys, is leave the matrices, there's an abstract there. Don't start writing out 3x3 and choose fill down. Just do capital. So the way I would start this one is capital A, capital and so you really just start with the check. Now you introduce your two vectors in. You go from there. Great.
Oh, excuse me, I need.
No, I know that's.
That's great. You just, now you just leave the punchline and you're golden. Okay, good. So it is a subspace.
Why is we still? I can't remember. I don't have it.
What is it about this that makes this thing work? Well, what it is that you transpose A plus B and it was the same as the negative of A plus B.
That's a streaming.
What's the membership card into this club? I get into the club, and if when I transpose myself, this is, I get the negative of myself.
Okay.
So I'm checking in here. I'm assuming that it was already true for A and for B, which are already members of the club. And now the question is, will A plus B still be a member of the club? To check it, we transpose it and we ask, does that equal the negative of both? We're gonna math to show that. Once you've written this out, you can just say, yep, it's an LS. We're good to go. And same thing here. And meanwhile, if anything along the way fails, it's game over. And the answer is no. You're not a member of the club. It's not subspace. So far, so good?
Yeah.
Okay, so maybe grab a new person to write the next please take turns with the markers, but you guys are doing great. Appreciate it. Good job.
Definitely an X. This one here, this is also totally correct. But if I got done looking at this and then I said to you, well, what about for 4x4? What about if they did four bar? Sort of redone. Same here. That would be fine now.
Negative version.
There is a more general way of saying this stuff that would be faster. So I like what you've done, and it's really good. But another idea would be to simply say that A transpose equals A, negative A, B transpose equals negative B. And then you could just say, if I do A plus B and I transpose that, right? Remember the properties? This is A transpose plus B transpose, which is negative A plus negative B. See what I'm doing here doesn't depend on what size the matrix is. Could be 3x3, could be 4x4, could be 5x5, but I'm checking all of this checks that yes, A plus B is still in S. You know what I mean? So, a lot of people don't like abstract that, like not seeing the details, but actually abstract is really powerful. Because in one fairly short write-up, I can kind of kill this problem for size matrix, whether it's 3x3 or larger. So just something to keep in mind. What you have here is. It works as a rating. I just wanna encourage you to embrace the abstraction. Okay, very good. I will let you keep going, and that picture looks great. Anybody need help?
Why?
Hey, yeah, what's up?
I have a quick question.
Yes, so we're.
They did line of the building, it's really why equals.
I assume. Oh, no. I watched them. You'll have. The big issue here.
Yeah.
Down here, portion of the ladder, place the A with 0. But the second.
We wanna be able to get
It is, then it's not in the set. Because the matrix changed to a 5. Well, that's right, 0x cubed plus 0x, that is the 0.
I'll look it up.
That.
Looking it up. Still recording, it's still recording.
We're just been blocking it. We're blocking. They can't even see what we're doing.
If you can't, it's more negative than one like. I.
That doesn't make sense. Because the camera is moving. It's gonna be 0 vectors.
Yeah.
You have to do it. Right now, I'm giving. Oh, wait, let's see if it fails, yeah. Oh, it does fail. Oh, push the thing about first. Okay. A, yeah. We only that group where. I believe. Like, yeah, like we actually got it out. Like, oh, yeah, right. Everything was so. But we also are. Yeah, but we should. Okay. So we got. Eraser. I do like five friends. If you plug in zero, they all use zero. No, I think it's right. Is that what that's? Cool. And the next one.
No space.
We just say that it's the form A X equals 0. What is B?
B is hard.
So I know you have an
B, okay, yeah.
Notice I didn't write out.
X, Y, Z, and then,
It's just like. I don't know, like,
Yeah, so you would just, this is like. Arbitrary. You would just multiply the K all the way to.
minus Y. Plus B.
And you look at this,
And
is that in the same?
minus
Or
4X.
have a simple measure?
Different equation.
They just have to say that.
Minus
check mark.
Plus Y. And.
Was it done?
Yeah.
Are you? You guys are all together. So what? Are seeing the Y vector? I know. Closure what? Right, so the actual graph of it. Of course you care. Yeah, the actual graph of this X.
And then.
You guys have that. Just making sure you have. Kind of like that parabola. Okay, great. I'm happy with that. This one, you should be able to do it in less than 1 minute.
Will you say that it's of the floor, AX?
Yeah, help your party out with that. It's a big X and it's big something on this part of the X and you put right? And then you just add them together and ball off of the X. That's kind of like that first. Example. Yeah. This one, I'm gonna give you 1 minute. Go fast. And if you need it, on the side, and you find your neighbor. Just. I'm just saying it.
Yeah. I just think.
Both sides, then you get sort of like, I don't know. Why, it's actually mentioned slime. So I guess what that's on. It's not this cheating. It's not. Give me I have those two. Yeah. You remember that we're out.
I'm just saying, you're already down.
One single. Doesn't matter on the next
Yeah, no, see, that's kind of what I was going for when I made it. But like, what he did in the video, I didn't know the video, it's still plus the
I think that we did hang out and we could, you know, it's fine. We can.
This was just like showing us and not things.
And also to the bar.
That's what this like, I thought was like, the story.
I think that's right.
That's right. Take a break too. Which one is? Oh, tea. It's always a yes. That's what's. Now, why is it a null space? It's a null space because both of the equations are equal to zero. So remember my video, spaces are just systems of equations where every equation is equal to zero. You can just say this is a subspace of the group space. Yes, that's what it's like. Well, when there's your testing. You're in space. You ever see from now until we have with rewrite the entire world, it's always closed under addition. It's always. You don't have to wait for reinventing. We don't have to find out. I verified it once and for all. Times a set S, which is a null space or an index. You just get to say, this is a subspace. We don't have to check it again, go through a million measures and standard multiplication again, because they did that once and for all. So that we can benefit from that going forward. Don't have. So yeah, I would want here, Mr. Reed, let's say S is the null space of this matrix. I want you to write the matrix. That's it. That's it. That's it. That's all you can say. I know.
No, that can't, it's too easy.
Hey, guys, everybody's attention here real quick. You guys are all doing really, really well on this, and I know that most of you haven't had a chance to go through all of these parts. But I do have something else I want to share with you in the last part of our class today. So if we could take just a short break until about 3:30 or so, I'm gonna give you about 8-minute break here. That'll give me enough time at the end to share one more thing with you today. But great job with however far your group got. I think that was awesome. And you can always read the solutions online if you didn't have a chance to. But let's go ahead and take a break from there. And Bryce, you had a question for me.
Yeah, would this be the proper way to like, say like, hey, no, it's a little bit, but there's a matrix and this zero?
Here's my solution to our need.
That's like. Gonna take my grade.
Anytime you see a null space of anything, it's always a subset. I do want to see right now as a matrix, but you don't really need to say anything else.
Like, is this, like, would this be appropriate?
It's not wrong, it's just, you don't really, well, actually, this is. This would have to have a sign reference. Okay. But, that's not wrong, but that's just not getting to the heart. Is this a subspace or not? The answer is, oh, it's a null space, so of course, yes, null spaces are always subspaces.
Cool.
How come? Because Dr. Anna made a video last week where he showed that anytime you have a null space of any matrix, it will always be closed under addition, closed under scalar multiplication, therefore making it a symbol. We don't have to keep going back every time we see another system of equations and check it again, or maybe now it's not true anymore or something like that. No, it will always be true because we've shown it once and for all. I've shown it once and for all. You guys took notes on it, so we have that confirmed. Does that make any sense?
Yeah.
Sweet. Go ahead and take a few minutes break and then we'll start things back up. Sorry.
I want to be super involved. Yeah.
Right there.
My criteria.
I haven't tried it myself, but I feel pretty confident about our shift. I say check out the one. I think it was either, I think I listed up and they were one. Wait, I just, no, I look. Walking out, toss the truck and go. But that one helped me. Yeah, look up for. Just look like, check out motion.
Thank you.
I'll send you.
We just. No, it's just just kind of one. Oh, yeah. This is from calendar. Yeah. Yeah. So like, if I do that. Like stuff. If I really should, like. Yeah. You know, and it's 0 to 5.
Okay, guys, I think I'm gonna go ahead and pick things back up here again if I could. I love all the chitter chatter. I'm so glad that hopefully you guys have found some folks that you can study with now and collaborate with. We're all kind of on the same team here, trying to learn this material. I appreciate your work on the group work. Keep in mind that if you didn't have a chance to finish the group work today, it's totally understandable. It's totally okay. I have the solutions to all of the group works in Canvas. So be sure to check them out, especially if you didn't get a chance to finish or if you're feeling a little shaky. These are really good practice problems. And of course, you're going to get more of that on the homework that's due on Thursday. But at least for now, you've had a little bit of practice with it now. I want to spend the last part of our class today, guys, going into kind of a new section. I meant to put kind of a new section header up here, which is really section 4.4, which is on something called spanning sets. And
We actually kind of previewed this a little bit last Tuesday before we had our midterm. You might remember that I was talking about, oh, what was it? I was talking about finding the volume of a parallelepiped, right? So, you know, we would do, I think we took something like the vector 1, 2, 3 and the vector 4, 5, 6. And then we took the vector 7, 8, 9. And I was just taking those as vectors and I was saying, well, those could be the row vectors of a 3 by 3 size matrix. And it turned out that these three vectors, well, the determinant was 0. You might remember this. And that just means that, well, we were able to kind of cancel them out in a linear equation. We were able to make an equation that canceled out those three vectors. And so I had introduced at that time this idea of linear combination. I'm just going to put this back on the board for you again. But here, so last week when I did it, I was specifically looking at vectors in R3. 3 slots, right? V1, V2, and V3, just vectors in R3. But now, just 1 week later, we can do the same idea, but in any vector space V. So these vectors here, this handful of vectors, let's say, V1, V2, V3, and so on, this is a handful of vectors in any one of my universes that I'm interested in. These could be a handful of matrices. They could be a handful of polynomials. They could be a handful of calculus functions. And I can build what I'm calling linear combinations of those vectors, right? A linear combination. So this is an expression you would have seen last week. Let me just put over here these C sub i's. These are scalars. Guys, take a look what I have here. C1 times V1 plus C2 times V2 plus C3 times V3. What operations do I see here in this expression? Like, what am I doing? I don't see any division. I don't see any subtraction. What I see in this box are 2 types of operations: addition and scalar multiplication. It's exactly what's in the vector space axioms that are up here, right? This is kind of the most generic thing you can build out of vectors in a vector space. This is so-called linear combination. So we're going to see these kinds of expressions a lot in linear algebra, where we write a bunch of vectors down and we put scalars in front of them, and then we start adding them together. It's called a linear combination. And in fact, if I take all possible linear combinations, meaning that I take all possible choices of scalars, C1, C2, C3, I get what we referred to last week as the span of those vectors. I get the span of those vectors. Let me give you a very simple example, and then I'm going to tell you what this has to do with anything we've been talking about earlier today. Let's just take the vector. Let's just say I only have one vector, and it's just the vector 1, 2. So n is 1, okay? And this is a vector that I can draw a picture of just in the xy plane. It's just this vector right here. Well, let me actually just draw it as a point, because it really is just a point. So it's just this point right here. So I have a question for you. If my vector space V is R2, right, the xy plane, is that point by itself a subspace? Let's see. So we've been doing this in the group work. We did it earlier today. What's the first question? The first question is, does it pass the 0 vector check? Right? We just start with that. So if this is the only vector that I have in my subset S, is the 0 vector check going to pass? I don't think so, because the 0 vector is not in the set. The only thing in the set is that dot, which is that point. It's not the 0. The 0 vector is down here, guys. The 0 vector is 0, 0. That's the vector that behaves like the 0 vector. So the point 1, 2 is not the 0 vector. So this vector by itself is not a subspace. But what if I take that vector and I start building linear combinations with it? Now, in the case of just one vector, my linear combinations will just simply be one term. I'll take the vector 1, 2, and I'll be scalar multiplying it by all manner of constants. C1 could be anything. It could be 2. Okay, so if it's 2, I'd get the point 2, 4. It could be 10, in which case I'd get the point 10, 20. It could be -1, which would give me the point -1, -2. Or it could be 0 times 1, 2, which would be 0, 0. What am I filling out by drawing all of these different scalar multiples of the point 1, 2? What is this going to make? What kind of a shape does that look like it's going to become? A line. It's going to become a line, guys. It's going to be this line right here. And so, in fact, the span of 1, 2, oh, that's totally different than just 1, 2. The span of 1, 2 is the line through 1, 2. It obviously is going to include that point that we started with, but it includes a lot of other points too, including 0, 0 now. Because remember, C1 could be 0. If I take 0 and scalar multiply it onto any vector, I'm just going to get 0, 0. So now I have a new question for you. Is the span of this point a subspace of R2? If I take the whole line, not just the individual point 1, 2, but the entire line that I obtained by taking the span, now do I have a subspace? Oh, I sure do. If I take any 2 points on this line, right? Maybe x, 2x and y, 2y. If I add 2 points that have that form, that would be 2 points that are here, right? There's x, 2x. Here's y, 2y, right? Whatever they are. If I add them together, right? I'm gonna get what? X plus y and 2 times x plus y. It's somewhere else on the line again. And so that is a subspace. And this is, in fact, one of the big results that I want to get across right now, guys, is that although a handful of vectors, right, although a handful of vectors grabbed at random are probably not going to form a subspace, if you take their span, if you throw in all possible linear combinations of those handful of vectors that you started with, by the time you look at everything that you get from doing that, you will have a subspace of the big universe V, right? This is a theorem. It needs to be written down. Let's make sure we get this down, right? The theorem is that anytime you take the span of anything, anytime you take the span of, say, the set V1 through Vn, this is always a subspace of V. You guys kind of get the idea. I like this stuff. I really do. I really do like this stuff. This is actually really, really cool. Guys, what are you doing when you form the span? What you're doing is you're acknowledging that the original vectors you started with might not have been closed under addition and scalar multiplication. So you make them closed? Oh, you start throwing in all possible ways of combining those vectors together. You just make a big pile of more and more and more and more linear combinations until eventually, in this case, you've filled out the whole line, right? Eventually, you've thrown in enough vectors into your set that they actually do become closed now. In fact, the act of taking a span is basically the act of closing up your vectors under addition and scalar multiplication. Exactly what it takes for S to be a subspace. This is the idea. This is the idea. So I've got another fast test for you. Another way to say a fast yes to something being a subspace, which is if you recognize that your set is a span. We said it earlier, if S is a null space of a matrix, you can just write that down. If it's a null space of a matrix, bingo, game over, it is a subspace. Dr. Annan proved in his video that that null spaces are always subspaces. You can just say that. You don't have to keep proving it every single time you see a new one. Null spaces are always subspaces. Well, I got another one for you now. Anytime you take the span of anything, it's always a subspace. I mean, I can do whatever I want, right? I could take, you know, as long as the word span is here, as long as the word span is there, I don't care what I do. Let's just, I don't know, 1, 2, 3, 4, comma, 5, 6, 7, 8. Just making stuff up right now. Literally making it. It's not even in my notes. Make it a span of whatever you want, right? This is a subspace of, in this case, these are 2 by 2 matrices. So that would be a subspace of M2 of R. Do I have to stop and check that it's closed under addition and scalar multiplication? No, I do not, because it says the word span in front of it. Okay. So on the next midterm, in about a month from now, if I give you some of these problems and I say, is S a subspace of V? And if you see the word span in front of anything, if it says span of whatever, then the answer is yes, it is a subspace. You don't even have to give it a second thought. You can just say that. You can just say, yep, S is a span. If it's a span of something, it's a subspace. Now, what's maybe a more interesting question is not to grab a handful of vectors and just sort of willy-nilly form their span. There's something else that's more commonly done. And what's more commonly done is actually to start with a subspace to begin with and try to distill it down into a set of vectors that would have spanned it. Let me say that again. We're going to start with a big subspace, S. And to help us understand how this subspace works, what we can attempt to do is distill it down into a small set of vectors, a handful of vectors that would have spanned it. It's like the DNA of in biology of our human anatomy makeup, right? Is that basically we're all built out of building blocks, which is our DNA. We can think of a subspace as being built out of this small handful of vectors. And our goal can be to try to find that spanning set. So let me just make a quick definition and then I'm going to attempt to explain how that works. So we say that V1, comma, V2, comma, dot, 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 up to Vn is a spanning set for S. If when we take the span of those vectors, so if we take the span of V1 and V2 and dot, 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 up to Vn, that it actually is the entire subspace S. Then we call these vectors a spanning set. And one of our goals, one of our questions here, and this one is an important question, is how can we find a spanning set for S, for a subspace S? Right, so let's ask that question, then I'm going to tell you how to answer it, and we'll do a couple examples. So how can we find a spanning set for S? We're obviously going to be coming back on Thursday and talking a lot more about this. This is not, this is in section 4.4. We're going to talk a lot more about this, but let me give you an answer to this question. How can we find a set of vectors whose span would be S itself? So there is a 3-step process that we can use to answer that question. I'm going to write down the process and then I'm going to do 2 quick examples for you before we wrap it up today. The first step in the process is that I need to write the general form of a vector in S. What does it look like? Okay, what does a general vector in S look like? Like over here, in this example, a general vector in S over here would actually look like this form right here. That's the generic form, x comma 2x. Everything on that line has the form x comma 2x. We could try to write down what is the form of a general vector in S. The second, and then I'm going to add something here using variables. And you'll see what I mean when I do an example. I'm going to show you an example in just a second. The second step is, and I'll explain how this works in just a second, we have to bust out the variables. Okay, and then the third step, I'll explain what bust out the variables means in just a minute. The third step then is to make a list of the vectors that remain. Three-step process.